morning, everyone. Do you have any questions about the homework? So I believe it's due on Monday or Friday, Monday, Sunday night, yeah. Yeah, you know, Sunday night makes sense, yeah, because you have nothing better to do on Sunday but work on my homework. But do you have any questions? Have you guys started doing it? Are you kind of far along through it? Any pitfalls, concerns, questions? Okay, looks like it was a very easy homework, so next time I'll make sure it's 10 times harder. Okay. All right, so any questions about last lecture? So we talked about finite difference methods. Most of you have seen this stuff, so it was just fairly more just covering things you know. Okay, so last time we left off with an example application on the advection equation, and we did a forward in time, discretization for the time derivative, and a central in space for the spatial derivative, and we tried to program it together. Then we ran out of time. We had a bunch of kind of strange issues going on. But today's lecture, we're going to go back to that problem. We're going to do it in more detail together, and most of today's lecture is going to be focused on Python, sitting together and discussing implementation issues, etc. Okay? So just to remind you of this problem, we have this advection equation, du by dt equals c du dx. We are going to come back to this equation later in class and discuss exact solutions and the meaning of what these terms, the meaning of these terms. But for the moment, just recognize that advection essentially moves an initial condition in time and space. Okay, so if you have a negative velocity here, this is going to move to the right, and if you have a positive velocity, this is going to move to the left, given any initial condition. So the exact solution is just the initial condition translated in space at any time t. Okay. And this was the discretization we used. We said we were not going to deal with boundary conditions. Today we're going to actually implement just periodic boundary conditions because we want our initial condition to just advect to infinity. So we had a Gaussian. Maybe today we'll try with a sine wave. And we want to advect it to infinities. And the best way to do this, rather than using a very, very large domain, we'll just use a reasonably sized domain and then use periodic boundary conditions. So essentially, a periodic boundary condition, think of it as like you're moving on the surface of the Earth, right? So the surface of the Earth is periodic. You start at a point, you move around, you're going to come back to the initial point. You can keep moving around. So that's what we're going to do. I'm going to turn my back towards you. Apologize, because I need to see the screen up there. And I'm going to I'm going to start a fresh notebook. I don't know if you still have the notebook from last time. But we'll just start with a fresh notebook. Okay, so I want you to open up your laptops and follow through with me, please. Okay. So I'm going to get a Jupyter notebook over here. And for those of you who cannot see very well, like me, instead of increasing the font, I'm actually going to import a new styling that will hopefully make things just look like they are a little bit bigger. Okay. So with this new styling, I can do things like this, for example. Okay. See how cool this is? So you can style your Jupyter notebook. That's kind of something on the side. And you're welcome to use, I will post these notebooks online. And to get this styling, you just get my, you just grab it from my GitHub repository and just get the style, the CSS style, and just embed it in your Jupyter notebook. And it will just change all the styling for you. Okay? So for those of you who haven't done Jupyter notebooks, you should know by now that you can mix text, math, and programming in between. So I'm going to try to do both of these things. So we will be solving the advection the linear advection equation, because the advection equation can be nonlinear. Can someone tell me how can the advection equation be nonlinear? So we had du by dt equal c du dx. That's the linear advection equation. Why? Because c is constant. So when do you have a nonlinear advection equation? Not constant how? So you could have c as a function of x, but that's still not nonlinear. So unless c is a function of u, of the advected quantity, so if you have u du dx, then that makes it nonlinear. Okay? Remember, nonlinearity is going to be with respect to the variable we are transporting. Okay? So even if you had x squared du dx, that's not nonlinear really. Okay? Okay. So we will be solving the linear advection equation. Okay? And so again, equation. I know this is a little bit boring for some of you, but just bear with me. We'll do it together. And we'll do frac partial u by partial t. And I'm going to change the notation a little bit. I'm going to use a negative sign in front of the spatial derivative. I know in the slides I used a positive sign. I keep kind of going back and forth. But I want to use a negative sign specifically here to remind you of the Navier-Stokes equations. Because the Navier-Stokes equations in non-conservation form, or even conservation form, you had d rho u by dt on the left-hand side, or du by dt on the left-hand side. And on the right-hand side, you had minus u dot grad u, right? So that negative sign, I kind of want to enforce that in your mind. So we're going to use this form. Now, in this case, if c is positive, the velocity, the flow is positive, that's then the signal, the information is going to move from left to right. Okay? If c is negative, then the information is going to move from right to left. Okay, right traveling wave, left traveling wave. Okay, so this is great so far. Let's see. Okay. So give me a moment, please. Displays. Okay. So let's go ahead and import some boilerplate before we define. Okay, so let's just kind of complete the description. Subject to the initial condition, ux0 is equal to u0 of x. Okay? The exact solution for this equation is given by, so if you don't remember the exact solution, it's just simply u of xt is equal to u0 evaluated at x minus ct. Okay? So what this is saying, advection, is that you just take the initial condition and just translate it. You know, at t equals 0, this is saying at t equals 0, your solution is u0x. That's just the initial condition. At t equal 1, the solution is going to be u0 x minus c. So that means you take the points located at x minus c and just move them to the right, okay? Or to the left, depending on the sign of c, okay? Great. Very beautiful, amazing solution. Okay, so let's get some numerical boilerplate out of the way first. And I kind of have, I wish I can just import these from somewhere, but I always import NumPy, Matplotlib inline. This little thing over here, I recommend you always use it because that is going to produce high quality plots for you, like PDF quality. Matplotlib as PLT, and animation because I want to create some animations here. Okay. Pardon me. All right, so now let's define the initial, let's start by defining an initial condition. So what do you guys want for an initial condition? Take, okay, so what do you want u0 to be? equation. Let's do a sine wave. Let's do a sine wave. Or, yeah, let's do a sine wave. You can experiment at home with something else. U0 of x equal to sine some frequency, sine omega x. Okay? So numerically, let's just, if you want to plot this, this guy, you declare a linear space. X is np dot lin space going from 0. So on the domain, okay, so we haven't defined that solution. Okay, subject to the initial condition on the domain, 0 to L. Okay. So we're going to take L equal 1, L equal 1, and then I'm just going to plot the solution right here. So this is going from 0 to L. I typically use lowercase for all my variables, except for L, because lowercase l is annoyingly similar to the number 1. And so it bothers me so much. So except for L, I use capital. Or you could put it like XL, or still it would look like X1. Seriously, like L and, well, at least, actually the styling here makes L look like, anyway, in your styling, L may look, if you're using Courier, your L is going to look like 1. And I'm just going to use 100 points to plot the initial condition, plt.plot, x, then u0, let's define u0. That's going to be equal to np.sine, and let's say omega is 2 pi, np.pi, so that's 2 pi times x. Okay. See how nice this graph looks like? Because it's scalable vector graphics. If we did not have SVG turned on, it's going to look like crap. It's going to be like all aliased and whatever. So, okay. So now let's just kind of define specifically a number of points for our numerical solution. I don't want to do it with 100 grid points. I want to start by doing it with just 21 grid points. So that gives me 20 intervals, correct? L equal 1. So that dx is L over n minus 1. We saw that in the last lecture. Okay? And we're going to declare our x space from 0 to L with how many points? N points. Okay? So that our solution actually looks like this. And honestly, to show things numerically, when you connect your points with a straight line, you may not be seeing the entire picture. I sometimes recommend that you actually plot using symbols. So, you know, if you plot using symbols, it gives you it fixes in your head that this solution is actually discrete. Okay? Okay. So now let's do one of the first numerical methods. Okay, so I'm going to do forward in time, central in space. So the scheme that we have used in the slides uses a forward in time formulation, right? Forward Euler, un plus 1 minus un over delta t, and uses central in space. So commonly we call this the FTCS scheme, forward in time, central in space. Okay? Okay, so what does the using a forward Euler method for the time derivative. And I kind of want your reports to look like this. I want you to describe what you're doing to me, even more text. I don't have much time on me right now to kind of dig deep and start writing more text, but I want your reports, if you're sending me a Jupyter notebook, I want it to be filled with explanations and discussions and, you know, using high quality math. Don't use just A times B using, you know, the text. Use LaTeX for your math, okay? So we using a forward Euler method for the time derivative and a central discretization for the spatial derivative. The FTCS scheme results in Okay, so begin equation and equation. Okay, I'm gonna cheat a little bit, and I'm gonna use my math type. So I showed this trick to Mokbel last year, and he was like, wow, this is cool. So what I'm gonna do, I'm gonna go into my math type. Let me show you my math type. If you're doing what do you call it, LaTeX, you can probably do this as well, but math type is so much cooler. Anyway, so I'm gonna try do something here. I'm gonna copy this actually as LaTeX. Okay, so I'm gonna copy this and just paste it in here. Get rid of some junk terms over here. Ta-da, look at that. Okay, so that is our FTCS scheme, forward in time, central in space. It is an explicit method, so let's go ahead and implement it. What did we say we want? We want to define a time step size. Let's start with just a number, 0.01 seconds, okay? End time, 3 seconds, let's say. And I always like to try to put the units, if the units are not complicated and I know them, I just kind of put the units in comments next to the numbers, okay? Wave speed is going to be 1.0, so that's going to be meters per second, wave speed, okay? And we said we were going to do, okay, so T, okay. And then I'm going to call the number, this C delta T over 2 delta X, we're going to call it CFL. And in a few weeks, we'll understand why. Some of you know what this means, but CFL is an acronym for 3 people, Courant, Friedrichs, and Louis, who first derived kind of the meaning of this number, but don't worry about that now, just call it a number, CFL. That's going to be C times dt over 2 delta X, okay? So you notice how I use repeated divisions, because I don't like to pollute my my syntax with parentheses, okay? Just like we did last time, we're going to declare a solution, a list, to maintain the solution, to put the solution in so that we can plot it over time. And the initial condition in the solution is going to be U0, okay? So this is going to give us U0. We're going to put U0 in it. And then while t less than t end, as long as our current time, which we start at 0, as long as current time is less than the end time, do something, okay? So the first thing we want to do is get your un, which is the old solution, and that's going to be sol minus 1. You remember the meaning of minus 1, so this is going to return the last entry in sol, okay? And then we're going to declare a u new, which is un plus 1, and that's going to be un.copy. We need to make a copy here because we need to create new memory for the new solution. If we said u new equal un, then both of these variables will be pointing to the same location in memory. So you change one, it's going to change the other, okay? Great. All right, so now to the crux of the matter, where we said, kind of threw in this formula. So first, let's decide on what we need for boundary conditions, okay? So this is our domain. Okay. Now, mathematically, how many boundary conditions does this problem need? Why? No. But how many derivatives do you have? One order 1. So you really only need one boundary condition to specify this problem. If you put 2 boundary conditions, you're going to overspecify it. So typically, the number of boundary conditions has nothing to do with the number of boundaries. At each boundary, you may specify a number of conditions. It has to do with the highest order of your spatial derivative. So for a diffusion equation, for example, second derivative, you need 2 boundary conditions. For an advection equation, you really need 1 boundary condition. And that makes sense, because advection moves in one direction in space, right? I mean, it may be going to another boundary, but then the what we really need is to specify this boundary. If we are moving to the right, we need to specify this boundary. Now, on the other boundary, typically you have an outflow condition. Okay, so that would be a condition on du by dx. Okay, so that's going to be a condition on du by dx. So if you think of a semi-infinite domain, in this case, you only have an initial condition and it's just going to move in space. Okay, but to accomplish this, we're going to be using periodic boundary conditions. Now, before we touch on periodic boundary conditions, forget about the boundary conditions. Let's focus on the interior points. Assume we have values over here. Okay, so in terms of indexing, in terms of our human notation, this is 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so what are we trying to accomplish in our for loop in this ui n plus 1 equal ui n plus c delta t, this guy, where we are going to go and visit every point, okay, and do this discretization. So let's try this out. So at u2 n plus 1, we're going to say this is u2n minus cfl, or c delta t over 2 delta x, times u3 minus u1, all at n. Okay, I'm gonna drop the n. Okay, and I'm gonna do this just to explain to you why I was using this this strange slicing u2 and then u minus 2 last time. That was a little bit confusing. And then u3 at n plus 1, same thing. Is going to be u3 at n minus c delta t over 2 delta x. That's going to be u4 minus u2, dot, 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 all the way to the last interior point, u7, n plus 1 is equal to u7 at n minus c delta t over 2 delta x, u8 minus u6. We are assuming we have values over here, u8 and u1. So forget about the boundary points. Let's just focus on the interior points. Okay, so now I could do a for loop for this guy. I could say I want to loop over each entry in the array and do the update. And that's completely legit. That's going to take you about 3 lines of code. Okay? But with Python, you can do this whole thing in one shot if you think of these operations as vectors. Okay? So rather than going this way, I want to go that way, kind of column-wise. I'm going to take this entire thing and say this entire list is equal to that list minus these guys. So what is this list? In terms of Python notation, that's u1, 2, minus 1. Agreed? Do you remember this from last time? So that is going to slice through the array. It's going to take the first point from the left, inclusive, all the way to the last point open. So it's going to give us these guys. So u1 minus 1 is going to give us the interior points. So this will be u1 minus 1 at n plus 1. These guys are the same, right? u1 to minus 1 at n. Okay? Makes sense? Great. Easy so far, because we have the same indexing here. So essentially, you're taking the new array equal to the old array, same points, minus, this is just a number, c dt over delta x. OK. So now, what are these points? u3, u4, u5, all the way to u8. What are these points in terms of Python notation? We want to start from, so if we say u0 is going to give us this entry, u1 is going to give us this entry, we want to start from here. So that's u2. All the way to what? If we say minus 1, it's going to put us here. So how do we get this really last point? You don't put anything. Okay? You don't put anything. Okay? Does this clarify this? I know you had a concern about that last week. Does this make sense now? Kind of this thinking of it column-wise. So we're taking this entire set. So essentially what this is doing is just a vector operation, taking this entire set equal to that set minus c delta t this set minus, now what about these guys? U1 all the way to U6. So yes. Or you could put 0. You know, you could put 0 here, but it's not going to make a difference. All the way to where we want this guy. So if this is -1, oops. If this is -1 open, you know, open bracket, this is -2, right? Because we want to go to U6. And that is the power of writing things down by hand. U and U. UN is UN. Yeah. Clear? Okay. All right, so 1 to -1 equal to UN 1 to -1 minus CFL, that's C dt over 2 delta x, times UN 2, so that's UI plus 1, minus UN minus 2. Okay? Okay. Now, what about the boundary conditions? So, yes.
Why do you set U equal to UN property?
Okay, so yeah, I'm just allocating. I could say this is numpy dot zeros, or this is numpy. But if I say that numpy dot zeros, how many zeros? I need to use n. So rather than a number of grid points. So rather than doing that, I just grab an array, and I already declared that array. I know its shape, its properties. I'll just use that to create a new array similar to it. Okay? And then just fill it out, right? Yeah. Okay. Okay, so now what do we do with the boundaries? Okay, so in practice, actually, yes, we do need to set the boundaries, and I'll qualify that in next lecture, discuss more details about the boundary conditions, the proper boundary conditions. But in this case over here, we want to use periodic boundary conditions. So what do periodic boundary conditions mean? There's no more colors in here. A periodic boundary condition in 1D, it means you're essentially on a circle or on a surface, right? So you start at a point, and then you just reproduce yourself. Or numerically, a periodic boundary condition means taking all of these points, taking this what it means is that this boundary is identical to that boundary. So in other words, if you look beyond point 8, I'm going to erase this, okay, here. Okay, so with periodic boundary conditions, really, this point is also point 1. And then beyond point 8, what are you going to have? You're going to have point 2, and then point 3, right? And then 4, all the way to 8. And then again, you know, point 2 and so on. Correct? Does this make sense? What about the left-hand side? This is really point 8. It's identical to point 8. So what are you going to have over here? Point 7. What are you going to have over here? Point 6, point 5. Make sense? That's, yes, it's a circle. Exactly. So now, this is where physical insight comes in. So I'll give you just a recipe for this problem, and then we can think about a recipe if the velocity is in the other direction. Because things are moving from left to right, what I really want is to compute this guy here. All I need is to compute point 8. And then once I compute a value at point 8, I'll just move it to point 1. And it will be identical. Okay? So how do we compute a value at point 8? So U8 n plus 1 is U8 at n minus C delta t over 2 delta x. We had UI plus 1, which is U9, let's say, okay, minus U7. But what is U9? 2. This is really U2. And that's it. Clear? Okay. Okay, so you knew at the last point, that's minus 1. Now remember, when you are not slicing like this, when you use a direct index, that is going to give you the last entry. It's not an open bracket. It is the last entry. So this is U8 in our example on the board. Okay, that's still UN at 8 minus CFL times, okay, now UN at 9, or in other words, really, if you add 1 to -1, that's going to give you 0, right? That's going to give you, no, hold on. There's a mistake here. This should be U1. Yes, this should be U1. Sorry. Minus UN minus 2. Correct? So that's U7, essentially. So in other words, this is U2 and this is U7. Correct? And then we simply say U nu 0, that's the periodic boundary condition, equal U nu minus 1. Okay? Set periodic boundary on the left, compute last point on the right using periodicity. Okay? Now we're done computing U nu. We're going to save it, U nu, and don't forget to update time. Now, just in anticipation of what's going to come later, U nu, what is the time level of U nu? So let's think of time levels. N equals 0, n equal 1. So n equal 1 is delta t, n equal 2 is 2 delta t, and so on. So what is the time level for U nu? Is it n or n plus 1? It's n plus 1. It's the new time. So if we were to act, and that is going to be important when you are trying to compare a numerical solution to the analytical solution, you want to pick the correct time. Okay, so think of this. We entered the loop t equals 0. Un, or at t equals 0, sol 0 contains the solution at time equals 0. Then we computed the solution at time equal t0 at 0 plus delta t, so n equal 1. So then solution 1 is going to contain the solution at delta t. Solution 2 is going to contain the solution at 2 delta t, and so on. So that's going to be very important when we're doing order of accuracy. Okay? Clear? Okay. So now let's see what this does. Okay. Okay, so it ran, it did something. Now the best thing to do in these situations is really to do an animation. And I'm just going to spit out some code here. I'm not going to go through the code. You can just copy it and learn from what I'm, just do whatever I'm doing here. So essentially, I'm just going to create a series of plots and animate them, okay? Okay, and then I'm going to load the video to show you the animation. Okay, so let me make the video, let's say, okay. So fig size, or just DPI. DPI equal 300, okay? And then I'm going to create a huge figure with better resolution. Let's do, okay? And then let's do here 640 by 480. Okay, aha, nicer. Okay, so let's see. Okay, the solution is advecting, but look what's happened. Okay, so it's advecting very, very fast. Let me animate it at a slower pace. Okay, let me create more frames. So in this case, the dots can be misleading. Okay. Let me see. Still. Okay, this HTML video sometimes takes a minute for it to. And I'm going to plot lines instead of circles or disks. Okay, so K means black, hyphen means solid line. Okay, Okay, you can tell from this last figure that something is off. But anyway, this is the initial condition. It's bounded between -1 and 1, okay? And the goal of the advection equation is to just move this sine wave indefinitely. It should remain a sine wave. It should remain bounded between -1 and 1, okay? Let's see what the numerical solution does. Look at the bounds. The bounds are starting to grow. Okay, they're starting to grow. They are starting to grow indefinitely. Okay, so that's a problem. Okay, CFL over 2 delta x. That is really a problem. So let's run it for longer. Let's say you want to do it for 10 seconds. Yes. Okay, and let's do this at intervals of 5. Okay. Okay, so still running. Really, creating the animation takes more time than solving the problem. Okay. Now you can tell it's actually just blowing up. What's happening, it's just increasing, increasing, increasing. And if you run it forever, it's just going to get worse and worse and worse and worse. And you could say, okay, let's change the time step size. What do you want to do? We can change the time step size. Maybe it becomes more accurate. Or we can change the grid resolution. What do you want? The grid. Okay, let's use more grid points. So Tim is saying, what do you want? Let's double the number of grid points, 41. Okay, let's do 41. And I'm going to run this for just like 3 seconds. Okay, and so now we're thinking, okay, maybe we're going to get a better solution. Okay, so look at that. This is the last figure. It's still kind of blowing up. It turns out, really, whatever you do in this case, your solution is always going to blow up. Even if you change your time step size, you decrease it, you increase it, whatever you do to it, the solution is going to blow up. And you can try this at home. You can change your grid resolution. You can change your time step size. So we can go with a smaller time step if you want. So let's do 0.001. And this is minus CFL. Okay. So this is going to take longer. The animation really is the kicker here. So while this is compiling, what I'm doing here really is I'm creating a plot for each one of the solutions, and I'm storing it as an image, and I am compiling those images into a video. Okay? So same thing happens. So it's interesting. It actually should get really much. So it's kind of stabilized. It's stable for a period of time, but look at that. Then it starts kind of growing and growing. And eventually, if you run it for long enough time, it's just going to blow up. Okay? So who wants to know why? Do you want to know why it blows up? I mean, it's funny. This is like the first problem we solved together, and it didn't work. So what the hell is going on? Okay. Pardon me? So we're going to do it together, and we're actually going to look at, so when we discretize, when we converted the true differential equation into a numerical form, we introduced an error, right? And that was the truncation error. So what I want to do now, I want to look at the combined truncation error between the time derivative and the spatial derivative. Okay, so last time we looked at just the truncation error for one type of derivative. What I want to do now is look at the combination of this truncation error and see what it means. Okay, so we'll start by, so we look at our initial differential equation, du by dt is equal to minus c du by dx. And I'm going to write this u dot equal minus c u prime. So prime is a spatial derivative, dot is a time derivative. Agreed? Okay. And our scheme said, our solution said, un plus 1 at I equal ui at n minus c delta t over 2 delta x ui plus 1 n minus ui minus 1 n. Correct? Okay. Now, what I'm going to do, I'm going to write the Taylor series for this guy, and that guy around point uin. That's kind of our reference point, right? I and n. Time level n, spatial point I. So what is ui n plus 1 around uin? It's uin plus delta t du dt, that's u dot in, plus delta t squared over 2 ui double dot n plus dot dot dot, bunch of other terms, okay? And the reason I didn't continue doing those because I know they're not going to be relevant. This term is going to be the most important term. Now ui minus 1 at n, this is going to be in space. Around uin is going to be uin. Okay, so let's do ui plus 1 first. It's going to be uin plus delta x ui prime at n, right? We're using prime because this is a spatial derivative, plus delta x squared over 2 u double prime in plus delta x cubed over 3 factorial u triple prime n I plus dot dot dot. Okay. Same thing for ui minus 1 at n. That's equal ui at n minus delta x ui prime at n plus delta x squared over 2 ui double prime at n minus delta x cubed over 3 factorial u triple prime I at n plus dot dot dot. Okay? So these are the 3 Taylor series of n plus 1, I plus 1, and I minus 1. There are cross derivative terms, but they're not going to be relevant here. Okay? So we can just focus on just substituting these guys into our discrete scheme. So now we take each term and put it up there. I wish I had another marker, different color. Okay, so what do we have for ui plus 1? We have, let me do it. Let's just do it right here. So ui n plus 1 is ui n. This is just bookkeeping right now, okay? Plus ui dot n, okay? Plus delta t squared over 2 ui double dot n plus, you could say order delta t cubed, okay? Equal, this is exact. This is all exact now, okay? Equal, now what is ui equal? Okay, uin minus c delta t over 2 delta x, 2 delta x. Okay, so what is ui plus 1 minus ui minus 1? Let's just do it here. So the difference is equal 0. These guys cancel out, right? Plus 2 delta x ui at n. Prime, yes, sorry. Prime. Plus 0 for the delta x squared term. Plus 2 delta x cubed over 3 factorial u triple prime n I plus dot dot dot. Order delta x to the 4th. Okay, so what do we get here? 2 delta x u prime n I plus 2 delta x cubed over 3 factorial u triple prime n I plus order delta x to the 4th. Okay? Okay, let's simplify things a little bit. UIN and UIN disappear. Yes. To the fifth, yes. Correct, because the even terms are going to disappear. Thank you. Okay, so UN, UIN, UIN disappear. Correct? And I'm going to divide by delta t. So this guy goes away. This guy goes away. This guy becomes 2. This guy disappears. Correct? It's divided by delta t. So what do we get? We get u dot I n plus delta t over 2 u double dot n. Gonna move the orders all to the right-hand side, equal to minus, now I'm gonna multiply this out, c over 2 delta x are gonna disappear, correct? So you get minus c u prime n at I, okay? And what about this guy? We have a minus term, c over, so 2, this becomes delta x squared, right? So this becomes c delta x squared over 3 factorial u triple prime n plus order delta t squared, and then delta x to the 4th, okay? We're not going to worry about those terms. Okay, so we're getting very close. Now, can you tell me one additional simplification we can make, or one additional observation that we can make? What is our governing equation? And that equation is valid at every point in space, every point in time. So really, you can write this equation correct? So this is our governing equation. This is our governing equation. What is the rest? The rest of the terms is what we have introduced from the numerical method. What this equation means is that what we are really solving is not u prime equal u dot equal minus cu prime. We're solving u dot equal minus cu prime plus a bunch of other things. Okay, let's do one additional simplification. So we have a triple derivative here in space and a double derivative in time. So let's convert this guy into a spatial derivative so that we only have one first order time derivative and everything else is spatial derivatives. So what does this term do? So our governing equation is u dot equal minus cu prime. So what is u double dot? It's minus c u dot prime, right? It's minus c u prime prime. That's going to be c squared u double prime. Makes sense? So I use the governing equation to convert the time derivative into a spatial derivative. Are you on board? I see some squinting. I didn't make any bold claims. I just said, hey, you know, this is a second time derivative. It's continuous. There's no discreteness in here. So I should be able to use the governing equation to replace the second derivative. And I can use the governing equation because it is the equation governing this system. So we have uin equal minus c ui prime n. That's our governing equation. Now this term, we move it to the right-hand side. We get a minus delta t over 2. Now what did we say u double dot was? Was c squared u double prime. Okay? Minus c delta x squared over 3 factorial u triple prime ni plus da da da. Okay. So this equation is actually the true continuous differential equation that we are solving using this method. So what we did here is we took the discrete form, that is, you know, we assumed it is true, then we used the Taylor series to recover a continuous version of this discrete formula. And the continuous version has other terms, has a second derivative, has a third derivative, and so on and so forth. Okay? So we're not solving, this is what we were supposed to solve. Instead, we are solving this plus a bunch of other terms. Okay. Now, there's a problem here that is going to immediately tell us why our solution is blowing up. So we said that a first derivative means advection. Okay? Go forward or backward. It's just advection. A third derivative is similar to advection. It's called dispersion, and we will study this later on. Essentially, it moves things at different speeds. Okay, dispersion. It's similar to advection. Okay, so dispersion is going to create wiggles for you. What does a second derivative do? Diffusion. So what is the goal of diffusion? Dissipate things. Okay. What is the sign of the coefficient multiplying the diffusion term? C squared is positive. Delta t is positive. 2 is positive. So minus this guy is a negative quantity. So you're multiplying diffusion. You have a negative diffusion coefficient. Doesn't that violate every law we know in nature? Negative diffusion. So if positive diffusion has the effect of shrinking things, negative diffusion has the effect of blowing things up. And that's exactly what you're seeing here. What you are seeing is the impact of this term, exactly this term. If you go and dig in and start to evaluate the rate at which the signal is blowing up, it's exactly proportional to this guy. It's because you have negative diffusion. Clear? It's amazing, right? This truncation error thing. Like you think, oh yeah, you know, we approximated this, it should just work. No, man, it's not going to work. There's going to be a problem if you don't quantify your truncation error or analyze it. Now, this is easily doable on linear equations. That's why we do linear equations. Something like this is very hard to do on the Navier-Stokes equations, for example. But still, it gives you insight. If you see your solution blowing up, and you could say, well, you know, I have a central scheme. And it just so happened that the combination of the forward Euler and the central scheme is what's causing this problem. Okay? Clear? Okay. All right. Let me try something else. Okay, great so far. If you want to see, so what this is showing is really the direct impact of this negative diffusion, and you can see it more boldly. So now, when you think about it, how can you make this blow up faster? You increase the speed or increase delta t. Okay. The impact of delta x is insignificant on this one. Okay. So if we change the wave speed at this same delta t, if we make the wave speed 10, oh man, this is going to blow up way faster. Okay. So let's just go to 2 seconds. And we'll update the video. Yeah, the animation thing is just really the slowest thing in Python, unfortunately. Look at that. It's just kind of, oh, done, gone. Okay? Okay. Now, let me see. Okay, So we saw how this term came about from this second derivative, okay, over here. From the second derivative, that implied a second derivative in space. Now, if we had a second derivative in space over here, they would have canceled out. But I want to play around now with a different scheme for you to show you how another scheme, just changing the discretization, is going to change the nature of your solution. So what if we do the following? Did you guys write this? Okay. What if now we do, instead of doing central in space, we are going to do backward in space, one-sided differencing in space. The reasoning is that, so advection is what's called a hyperbolic phenomenon. It essentially kind of moves in one direction, okay? So if the flow is moving in that direction, it makes sense to just, step in that direction, right? So information from the point, so you don't know what you're up against. You're just looking backwards, you grab the baton and you give it to the next person, you give it to the next person, right? And you move forward. And one of the arguments for this scheme is say, well, you're using information from the next point and also the previous point, but you only have information at the previous point. You don't have information at the next point because advection is one directional, right? So you're going from left to right. So why not say, okay, I'm not going to use ui plus 1. I'm just going to use ui. So essentially, rather than using a central derivative, use a backward difference, okay? So rather than saying du by dx at I equal, ui plus 1 minus ui minus 1 over 2 delta x. Remember, we chose this because it had the higher order of accuracy. But that means nothing if the solution is going to blow up. It's second order accurate, but solution is going to blow up regardless, whatever time step you choose, okay? So rather than doing this, so essentially if you look at a curve, if this is point I plus 1, and I minus 1, you're approximating the derivative here using these 2 points, okay? But the problem with advection is we don't know information at this point. So what if we just use these 2 points, I minus 1 and I? So in other words, we do du dx at I equal ui minus 1 over delta x. Okay, pretty simple. So all we have to do is change one term, 2 terms, 2 lines in our code. So I'm going to go ahead and copy this code and say, edit, copy cell, and just say, okay, so now forward in time, backward in space, or upwind also, upwind space, FTUS, okay? So this scheme, I'm going to write the math now because we don't have time. Okay, let me just copy all of these guys. I'll just reuse them. I know you can create functions and be very fancy, but that is not the goal here. Okay. Okay, so everything stays the same. Okay, everything remains the same, except for these terms. So what changes here? Rather than doing ui plus 1, I want to do ui. So what is ui? 1 to minus 1, right? That's the interior point. That's just it. 1, 2, minus 1. Now what about the boundary point? We don't have this guy. This guy is 0, correct? So we don't have point 2 anymore. We just have point, sorry, this is minus 1. Apologize. Yeah. So that's ui minus 1. Correct? That's u8 minus u7. Okay? All right, so let's run this guy. Gonna keep the, just let me increase the timestamp size for a second. And this is not FTCS, this should be FTUS. Okay. Okay. Oh, look at that. We still have a signal. Much better results. Okay, so let's see how the solution behaves. Okay, let's run it for longer, a little bit longer, maybe 6 seconds, and do 8, skip every 8 frames. Okay, let's run this. Still hasn't updated. So sometimes this HTML thing doesn't update in time. Stupid thing. Okay. Spring lectures, finite difference, FTUS. Okay. Let's see. Oops. Okay. Wow. Still. Why is it working? T-end is 6 seconds. Oh, maybe I guess we didn't run it. We didn't run the 6 second. I thought I ran it, but I didn't. Okay. Okay. Now what is the first thing you observe? It's shrinking, but it is stable. That's a big deal. It's stable. It didn't blow up, but it's shrinking. Okay, it is shrinking. Okay, do you think you can do the same analysis here? See what happens. So what do you expect without doing the analysis? What do you expect the first term in the true differential equation we're solving? So if you had u dot equal minus c u prime. What is the nature of the first term here? Positive diffusion. Yes. See, this is the insight we're after. I don't care about you knowing fancy math and programming. You need insight. Without insight, numerical solutions are useless. Now you have insight. You have a positive plus a k squared u double prime. That's what you have with this Upwind scheme. Okay? And you can derive this using the same procedure. Okay? So the true equation we're solving is this equation plus a bunch of other terms. Okay? Let's play a little game. Okay. So we said that our new scheme is ui n plus 1 equal ui. Well, not a little game. Let's see where this analysis leads us, because I am after the coefficient in front of u double prime. Okay? Let me think if I should do it in class or have you do it in the homework. Okay. Let's just do it in class. Okay. This is uin minus c delta t over delta x. Remember, this is first order, one-sided, so you have adjusted delta x. And you have uin minus ui minus 1n. Okay? Then we do the same procedure. We substitute. You have uin plus delta t u double dot, u dot in plus delta t squared over 2 u double dot n plus dot 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 equal uin minus c delta t over delta x into uin. So let's keep this guy minus plus c delta t over delta x. So minus minus, you have a plus. And what is ui minus 1? Actually, let me just keep them inside the parentheses. Minus c delta t over delta x into uin minus what is ui minus 1? So you have a minus uin, correct, plus delta x ui prime n minus delta x squared over 2 u double prime in plus dot, dot, dot. Okay? I'm not going to carry any higher order terms because I know they're going to be insignificant. Okay. uin disappears. uin disappears. They cancel out. Delta t, delta t, delta t. Correct? Okay. So we have u dot in plus delta t over 2 u double dot in. We still have this term. Equal. Did I make a mistake here? No. Minus c u prime in, correct? Delta x and delta x cancel out, correct? Plus c delta x over 2 u double prime in plus dot, dot, dot. Okay? So now we recovered our original equation. This is a spatial term. Let's just convert this guy into a spatial term. And we know that u double dot equals c squared u double prime. So we get ui dot n plus delta t over 2. U double dot is c squared u double prime, correct? Equal minus c u prime in plus c delta x over 2 u double prime in plus dot, dot, dot. Now, uin equal minus c ui prime n. That's our original equation. Now, this is the fun part. Plus c delta x plus 1 over 2 c delta x minus c squared delta t u double prime in. So let's take c outside. You have c over 2 delta x minus c delta t u double prime plus dot, dot, dot. Okay. So you said we're going to have a positive diffusion term. It's only positive when this guy is positive. The coefficient is positive. So in other words, when delta x minus c delta t is greater than 0 or equal to 0, and then you could put a condition on delta t or on delta x. Okay, you could put a condition on either. You could say, oh, then I want delta x to be greater than c delta t, or c delta t. You know, you could change the condition in any way you like. Okay. Did I miss a term here? Now, one fancier way of doing so this is the condition. So let's try to violate this condition. Okay. Let's say you want to make sure that your delta x is greater than or equal to c delta t, or in other words, c delta t over delta x is less than or equal to 1. Okay? So I'm going to pick delta t such that it violates this condition. Okay? So in other words, delta t, I want to pick delta t to be greater than delta x over c. Okay? So let's do that. So I'm going to put delta t. So, okay, so at this point, c times dt over dx, what is it? It's 0.4. So it's less than 1. Okay? Then what if I pick dt to be equal to dx over c? Okay? Dx over c plus 0.1. Okay? Or in other words, 1.1 times dx over c. Let's run it. Let's look at the solution. We predict that, so it didn't blow up. again. Hold on. Okay. Print. Let's just do 1.1 times dx over c. And then yeah, so it is 1.1 CFL C. I made a mistake here. This should be c dt over dx. Okay, I apologize. All right, so that's the mistake. So now this should blow up. It should, there you go. It just blew up. Okay? Makes sense because we made this diffusion coefficient negative. This diffusion coefficient used to always be negative, to positive. Can I make the diffusion 0? How? Yeah. Set c dt over dx equal 1, or c dt equal delta x, or dt equal dx over c. So let's do that. Then you will have, this is the only case that actually I know of that you get an exact solution numerically. Exact solution. Your error is 0. Your error is exactly 0. So let's set dt equal dx over c. See what happens. Look at that. It's just going to advect forever. Okay? Whatever time step you choose, whatever spacing you choose, I guess they have, as long as they're consistent in this way. So let's do this. Okay. This is great, right? This is insight into how you rip through a numerical method. These are very rudimentary analyses, elementary, but they have so much insight. If you cannot explain typically a complex system, you should be able to identify, as you develop expertise in CFD, you don't have to go through fancy analyses to describe what's going on in your solution. Oftentimes you meet people who look at your solution like, yeah, just increase your diffusion coefficient, or use a Upwind scheme over here because this is doing that. And you're like, well, how did you know? Well, it's because you have experience with these things. You can understand the simplest features of numerical methods. I mean, we can go and start doing eigenvalue analysis, and it's just so abstract. It's not going to give you the insight that something like this gives you. Okay? And besides, you can't really apply this kind of stuff on nonlinear systems. You have to do like complex eigenvalue analysis and kind of do it on the fly, and good luck getting physical insight on those systems. Okay? So let's just run the animation here. Oh, what? Something's going on with this. Okay. Look at that. There's 0 error. Well, it turns out that all the higher order terms are multiplied by powers of this guy. Very good point. I'm going to call you the truncation error man, because you're always kind of spot on these higher order terms. You're absolutely right. So what it does make a difference. What Aaron is saying, well, how come you're getting an exact solution? What about all the higher order terms? Well, the reality is if you carry the analysis, if you carry all the higher order terms, they will all be powers of this guy. So, and given that delta t, the dx over c is a root, it's just going to make all of the other terms go to 0. Okay? All right, so I'm going to finish off here. I was going to do the advection diffusion equation, but I think what we did today hopefully was very helpful. Many of you have done this before or have seen it. Hopefully, today's lecture gave you slightly different insight into doing things. Always go to the simplest form. Do not complicate things. Just start, something is confusing you, just write it down and think of it in a different way, like we did with the indexing, with the slicing. So in my mind last week, I always kind of know how to do it because I thought about it a long time ago, but then you guys asked, like, how are you doing this indexing? So I had to really write it down and think about it that way. Always write it in simple forms. It's not shouldn't be beyond you to just kind of write it down, think about it in the simplest of forms. Dissect, rip a problem apart into its simplest form, okay? Just like we did here today. Next week, we're going to combine advection and diffusion, and we will see how the central scheme, we can stabilize it by adding diffusion. So we can stabilize this negative diffusion by adding more positive diffusion, stronger positive diffusion, to kind of combat that, okay? And then you can start playing games like saying, okay, what if I add just the right amount that combats the negative diffusion? Then you're going to start seeing other terms show up, like the third derivative terms, which are going to cause wiggles in your solution, okay? So we will do the advection diffusion equation next Tuesday, which is a model equation for the Navier-Stokes and for the vorticity stream function formulation, which we will hopefully get to next Thursday, okay? So good luck with your homework for Sunday. I'll probably release a new homework today or tomorrow. So essentially asking you to do this in 2D, for example. Just try it out in 2D and see what happens, because we want to be doing things in 2D. The indexing, the slicing in 2D is the same. You just have two items in the bracket. So in the x direction and the y direction, okay? All right, good luck.